In this experiment, I am letting water flow out of a hole. And of course, the water falls to the ground because of gravity. If you notice, the cup doesn't leak when it's in free fall. This is because the cup and the water are falling at the same speed, almost as if they are stationary on the ground. Nothing unusual, right? Watch carefully. The magnet is pulled up by the whiteboard, which suggests that gravity is weaker than the magnetic force between the magnets and the whiteboard. Now let's talk about frames of reference, because it is essential to understanding relative motion. In this video, we see a ball following a straight line path to the ground. Now in this video, the ball is following a parabolical path to the ground. This is because the frame of reference changed from a moving one to a fixed frame outside the travelator. So the ball was never really moving in a straight line. What you see here is two cameras filming the same situation but from different frames of reference. The view from the first camera suggests that everything is moving backwards, and the view from the second camera suggests just the car is moving forwards. This is something we experience in everyday life. Think about when you sit on a train. The scenery moves backwards and you move forwards. Now let's dive into explaining the definition of gravity. To help, here's one last experiment. As you saw, the car accelerated forwards while me and the bag moved backwards, almost as if a force is pulling us backwards. We know this force doesn't exist. These experiments lead us to believe that gravity is not a force, but a consequence of acceleration. But wait, if gravity is not a force, then what is keeping us from jetting off into space? The Earth is constantly moving through time and space and is always accelerating upwards at a constant speed of 9.8 meters per second squared. So what I'm saying is that Newton's apple didn't really fall. Yes, it broke off from the tree that it was growing on, but during the period it was supposedly falling, it was actually in the same place, or free fall, and the Earth accelerated upwards, catching the apple. Of course, from Earth, we saw the apple fall towards the ground because the planet is substantially bigger than the apple. Don't worry if you can't imagine it, because even Einstein took 7 years to explain it and said the only way to really show it is through complex mathematical equations. Even today, gravity is the intuitive force. If you have to fly Apollo 11 to the moon, you would look at Newtonian physics. However, GPS tracking uses general and special relativity as explained by Einstein. In 1919, a solar eclipse occurred that proved Einstein's theory. Newtonian physics says that light travels in straight lines or rays, while Einstein's theory says that light is bent because of large bodies of mass that curve spacetime. So here is where Newtonian physics predicted a star would be placed. And here is where Einstein's theory predicted the star would be placed. Back to the solar eclipse. The eclipse showed the correct position of the star because the sun's light was blocked by the moon in front of it. Even though Einstein's prediction was off, it was close enough to prove his theory. So now I would like to end by a quote by John Wheeler. Matter tells spacetime how to curve, and spacetime tells matter how to move. Thank you.